Module 8, Lecture B, Tabulation Patterns. By the end of this lecture, you will be able to design bottom-up DP tables that capture subproblem states and transitions, implement tabulation-based dynamic programming algorithms in Python for classic problems, and analyze and optimize the time and space complexity of tabulation solutions. Designing DP tables. DP table dimensions. When building a bottom-up dynamic programming table, the key first step is to decide how many dimensions the table needs and what each one represents. These dimensions should match the subproblems, with each index describing a specific state whose answer you want to store. If the state depends on a single parameter, such as a position in a sequence, a one-dimensional table is enough. If it depends on two parameters, like two indices in a string or time and budget, you use a two-dimensional table. For more complex problems, such as scheduling across multiple machines, you may need 3 or more dimensions, as long as each dimension corresponds to a meaningful part of the problem state. When designing a dynamic programming table, choose dimensions that represent the key variables defining distinct subproblems that you will reuse. In text comparison, this often means using prefixes of the two documents as the two axes. In financial planning, time and available funds can serve as the table dimensions, while in grid navigation, row and column positions work naturally. In every case, each dimension should correspond to a meaningful incremental change, such as adding a character, moving forward a year, or taking a step, so the table accurately and efficiently captures how the problem evolves. When designing a dynamic programming table, you need to balance how expressive it is with how practical it is to compute and store. Each extra dimension increases memory and time costs, so you should look for ways to reduce dimensions by understanding the true dependencies in the problem. For instance, you might track only the current city and remaining fuel instead of total distance, or simplify recommendation problems by aggregating time or pre-computing user features. By avoiding unnecessary dimensions, you create a manageable grid of subproblems that remains both comprehensive and efficient to compute. Python code, DP table dimensions. In this lesson, we focus on how to choose dynamic programming table dimensions for a simple path counting problem. We compare using a one-dimensional table with using a two-dimensional table, and explain when each design is appropriate. For each approach, we clarify how every table index corresponds to a specific subproblem, so that each entry represents a meaningful state in the overall counting process. The goal is to make the connection between table structure and subproblem definition clear and intuitive. The comment about installing NumPy, Matplotlib, and Seaborn is simply a suggestion that these libraries can be helpful for more advanced data manipulation and visualization tasks. However, they are not required for the simple script being discussed. The current example is intentionally limited and focuses only on basic dynamic programming ideas. In other words, the libraries are optional tools for more complex work, not a dependency for understanding this demonstration. We begin by setting the grid size to 3 rows and 4 columns, measured in feet. These dimensions define the layout of the grid and serve as the basis for our calculations. Using this setup, we can build tables for a dynamic programming approach. These tables will help us systematically count the number of possible paths through the grid. To solve the grid path counting problem, we set up a two-dimensional dynamic programming table. This table is a list of rows, and each row is a list of zeros, whose length matches the number of columns. Initializing all entries to 0 prepares the table to store the number of paths to each cell. Using this two-dimensional structure makes it easy to reference and update the path count for any cell based on its position in the grid. To begin building our two-dimensional dynamic programming table for counting paths, we set every cell in the first column to 1. This reflects the fact that there is only one way to reach any position in that column, by moving straight down from the top. Doing this establishes the base case for the problem and ensures that each cell in the first column correctly records the number of paths leading to it. We start by filling the first row of the two-dimensional dynamic programming table with ones. This row represents the base case for our path counting problem. Each cell in the top row has exactly one way to be reached, by moving only to the right from the starting position. These initial values provide the foundation for computing the number of paths to all other cells in the table. To fill the two-dimensional dynamic programming table, we compute the number of paths for each cell starting from the second row and second column. For any given cell, the number of paths to reach it is the sum of the paths to the cell directly above and the cell directly to the left. This works because any valid path to that cell must come from one of these two directions. By applying this rule to every cell, we account for all possible paths through the grid. The code prints a message to explain that it is about to display a two-dimensional dynamic programming table. This table shows how many paths lead to each cell in a grid. Each pair of indices in the table corresponds to a specific cell and its path count. The message clarifies the table's purpose, so it is clear that it represents path counting information for the grid. We go through each row of the two-dimensional dynamic programming table, and for every row, we output its index followed by all the values in that row. This gives a concise snapshot of the table's state. It shows how many paths reach each cell while keeping the printed output compact and easy to read. We begin by setting up a one-dimensional dynamic programming table that represents the number of paths to each column in the first row of the grid. Each entry in this table is initialized to 1, meaning there is exactly one way to reach any position in that first row from the starting point. This initialization serves as the base case for the dynamic programming method. Using these initial values, we can then build up the number of paths for all subsequent rows in the grid. We update the one-dimensional dynamic programming table by iterating over the grid row by row, starting from the second row because the first is already set. Within each row, we move from the second column onward. At each position, we add the value from the previous column in the same row to the current cell. This accumulates the number of paths coming from the left and uses previously computed values so that each cell ends up storing the total number of paths that reach it. We now display the one-dimensional dynamic programming table, which shows the number of paths to each cell in the last row of the grid. Each entry in this table represents how many distinct paths reach that final position. By looking at these values together, we get a concise summary of the overall solution to the path counting problem. We use a one-dimensional dynamic programming table to store the number of paths to each cell in the last row of the grid. All the values in this table are shown together in a single line for a compact view. The final value in this line corresponds to the last cell of the grid. This value represents the total number of paths to reach the bottom right corner. This script shows how dynamic programming can be used to count paths on a grid. It first builds a two-dimensional table where each cell stores the number of ways to reach that cell from the top left, starting with ones along the first row and column, and then filling each remaining cell as the sum of the values above and to the left. The completed table reveals the number of paths to every cell. The script then demonstrates a more space-efficient version that uses a one-dimensional table to track the number of paths in the last row, updating values in place. The final entry of this one-dimensional table gives the total number of paths, highlighting the trade-off between clarity and memory usage in dynamic programming solutions. Initializing base cases. When building a dynamic programming table, you begin by setting the base cases, which are the simplest versions of the problem that you can solve directly. These base cases act like initial conditions and define what happens at the smallest input sizes or boundaries. They are crucial because every later value in the table is computed from them. If the base cases are wrong, all subsequent results will also be wrong, so they must be chosen and set very carefully. To identify base cases in dynamic programming, think about what happens when the problem size is reduced to its minimum. For example, if you are processing items, ask what the outcome is when there are 0 items. In optimization problems, this often means 0 cost or profit, while in counting problems, it can mean there is exactly one trivial way to do something, such as an empty schedule. In real-world terms, base cases often represent having no remaining resources, like budget or time. By examining these edge situations, you can define clear initial values for your dynamic programming table. In dynamic programming, base cases are not always single cells. They can cover entire rows or columns, especially along the edges of the table. For instance, you may need to initialize all states that represent 0 time or exhausted resources, since no further actions are possible from those points. Different boundary regions can require different starting values to capture conditions like having no vehicles available in a logistics problem. Defining these boundary indices carefully ensures that each computed value builds on a correct foundation and that the table accurately reflects the structure of the problem. Python code, initializing base cases. In this lesson, we focus on how to set up the base cases in a simple dynamic programming table for counting the number of ways to make change with coins. We initialize the base row and base column so they represent the simplest subproblems, such as making 0 amount or using 0 coins. These base entries act as anchors that all later table values build on through the recurrence. By printing the table with clear labels, you can see how the initial base cases directly influence and determine the remaining states in the dynamic programming solution. This script does not require any pip install commands because it only uses standard Python libraries. That means the code is completely self-contained and has no external dependencies. As a result, you can run it in any normal Python environment without extra setup. This lets you focus on understanding the algorithm itself instead of managing additional library installations. To solve the coin change problem with dynamic programming, we first fix the coin denominations we are allowed to use. In this case, the available coins have values of 1, 2, and 5. These specific values define the building blocks we can combine to reach any target amount. Setting this list of denominations provides the foundation for the dynamic programming method that will compute how to make change. In this coin change problem, we set the target amount to $5 and represent it in cents. Using cents lets us work with whole numbers instead of decimals, which simplifies the calculations. This integer representation is important for the dynamic programming method because each unit in the algorithm corresponds to a single cent and helps maintain precise results. To solve this coin change problem with dynamic programming, we first build a two-dimensional table. The rows represent each coin option, plus one extra row for the case where no coins are used. The columns represent all amounts from 0 up to the target value. We initialize every cell in this table to 0, creating a grid that we will later fill with the number of ways to make each amount using the available coins. To set up the base case for our dynamic programming table in the coin change problem, we initialize the first column of each row to 1. Each row represents a coin option, plus an extra row for using no coins. Setting the first column to 1 encodes the idea that there is exactly one way to make a target amount of 0 cents, by choosing no coins at all. This base case is essential because it provides the starting point from which the rest of the table, and thus solutions for larger amounts, are built. To set up the base case in our dynamic programming table, we consider the situation where no coins are available. For every column that represents a positive amount of money, we place a 0 in the table. This 0 means there are no ways to make that amount of change without using any coins. Establishing this initial condition gives us a clear starting point for all later calculations that do involve coins. To fill the dynamic programming table for the coin change problem, we process it row by row, where each row corresponds to a coin type and each column to an amount up to the target. For each cell, we first take the number of ways to form that amount without using the current coin, which comes from the cell directly above. Then, we add the number of ways to form the amount by including the current coin, which is taken from the same row at the column representing the current amount minus the coin's value, if that amount is non-negative. If the amount is smaller than the coin's value, this second contribution is 0. The sum of these two quantities gives the total number of ways to make that amount using all coins considered so far. We begin by creating a header list to label the columns of a table. The first label is the word amped, short for amount, to show that each column corresponds to a money value. Next, we use a list comprehension to generate labels for every amount from 0 up to the target amount, by converting each number in that range to a string. Finally, we join the initial amped label with this list of amount strings to form a complete header row that clearly marks each column with its specific amount, including 0. The code prints the header row of the dynamic programming table by combining all header entries into one space-separated string. This creates a single compact line of text. As a result, the amount values are clearly displayed across the top of the table, making the output easier to read and interpret. We iterate over each row of the dynamic programming table, where each row corresponds to a particular coin choice, including the option of using no coins. For clarity, we label each row with the letter C followed by its row number to indicate which coin or combination it represents. We then collect the values in that row, convert them to strings, and print them. These values show how many ways we can make each amount using the coins considered up to that row, making it easy to see how the base cases shape the rest of the table. This script shows how to build and fill a dynamic programming table to solve the coin change problem. It uses coin denominations and a target amount, converted to cents, with rows for coins and columns for amounts from 0 up to the target. The base cases set all entries in the 0 amount column to 1, meaning there is one way to make 0, and set the first row for positive amounts to 0, meaning no ways to make change without coins. The rest of the table is filled using a recurrence that combines ways of including and excluding the current coin. Printing the completed table with labeled rows and columns helps visualize how these base cases propagate to form the full solution. Linking indices to subproblems. To understand dynamic programming tables, think of each cell as representing a specific subproblem rather than just a number. Each index answers a clear question about a smaller part of the overall task. For example, a cell might store the best score for aligning parts of 2 DNA sequences, or the minimum cost of serving customers with vehicles. By clearly defining what each index means, you know how to fill in the table and how to interpret the results. This makes the table a structured representation of how the original problem is broken down. When designing a dynamic programming table, treat each cell as the answer to a specific question about the problem. For instance, one index might represent how many items or years you have considered, and the other might represent a resource like time, budget, or capacity, with the cell storing the best achievable outcome under those limits. By clearly stating in words what each index and each cell means, you can check that you have included all important aspects, such as constraints or risk. This habit helps ensure that your table structure truly matches the requirements of the problem you are trying to solve. When designing indices for subproblems, make sure that moving from one cell to another in your table corresponds directly to meaningful decisions in the original problem. A transition should naturally represent actions such as including an item, moving to the next time step, or assigning a task. In route planning, this might mean one index tracks the current city and another tracks which cities have been visited. So, each move represents traveling to a new city. In text processing, indices can mark positions in the document and in the pattern, with transitions showing progress in one or both. Overall, the indices should capture where you are in the problem, and their transitions should mirror the steps needed to build the full solution from smaller pieces. Python code, linking indices to subproblems. In dynamic programming, it is important to link each table index to a clear subproblem meaning. A simple way to demonstrate this is with the coin change problem, where one index can represent the target amount and another index can represent the number of coins considered. Each cell in the table then answers a specific smaller question, such as how many ways we can make a certain amount using a certain set of coins. This shows that every entry in the table corresponds to a well-defined subproblem, which is the key idea behind dynamic programming. No external libraries are needed for this basic demonstration. We will work with standard United States coin denominations measured in cents: 1 cent, 5 cents, 10 cents, and 25 cents. Using only these coins, our goal is to solve the coin change problem. In other words, we want to determine how many different combinations of these coins can be used to make a given total amount. In this problem, we set our target amount to 10 cents. This target is the total value we want to reach using different combinations of coins. With this goal defined, we can now focus on counting how many distinct ways we can make 10 cents using the available coin denominations. To solve the coin change problem with dynamic programming, we build a two-dimensional table that tracks how many ways we can make each amount with different sets of coins. Each row represents using a certain number of coin types, and each column represents a specific amount of money. The table is sized using the number of coin types plus 1 for the rows and the target amount plus 1 for the columns, and it is initially filled with zeros. This structure lets us systematically compute the number of ways to form every amount up to the target using the available coins. To set up the base case for our dynamic programming table in the coin change problem, we initialize the first column for every row to 1. Each row represents a different number of coin types, and the first column corresponds to a target amount of 0. Setting these entries to 1 encodes the idea that there is exactly one way to make an amount of 0 by choosing no coins at all. This base case is essential because it provides the starting point from which we build solutions to larger target amounts. We solve this problem by looping through each coin type and for each one considering every amount from 1 up to the target. For a given coin and amount, we compute how many ways we can form that amount without using the current coin, and how many ways we can form it if we do use the current coin, provided the amount is at least as large as the coin's value. We then add these two quantities and store the result in our table. By repeating this for all coins and amounts, we build up the number of ways to make each amount using the available coin types. We focus on a specific entry in the dynamic programming table by setting the row index to 2, meaning we only use the first 2 coin types, and the column to 7, meaning we want to form 7 cents. The value stored at this position tells us how many different ways we can make 7 cents using just those 2 types of coins. Interpreting the table in this way shows how each entry corresponds to a smaller subproblem within the overall dynamic programming solution. The row index tells us which coin types we are allowed to use, up to and including the coin type indicated by that row. The column index tells us the exact amount of cents we are trying to form. The value in a cell then gives the number of different ways to make that specific amount using only the allowed coin types from that row. Altogether, each cell represents a subproblem. Using coins up to the given row, there are a certain number of ways, given by the cell value, to make the amount shown by the column. This script illustrates a dynamic programming solution to the coin change problem using a table whose rows represent coin types and whose columns represent amounts up to 10 cents. It fills the table by considering, for each cell, whether to include the current coin type or not, starting from a base case where there is exactly one way to make 0 cents. Each cell then represents the number of ways to form a specific amount using only a subset of the available coins. For instance, one cell shows there are 2 ways to make 7 cents using just the 1 cent and 5 cent coins. By printing these interpretations, the script clarifies how each table entry corresponds to a smaller subproblem, showing how dynamic programming breaks the overall task into manageable parts. Tabulation practice problems. Knapsack tabulation basics. In the knapsack problem, you are given items with weights and values and a maximum capacity, and you want to choose items that give the highest total value without going over that capacity. A tabulation or bottom-up approach solves this by building a table where each entry represents the best value achievable for a certain number of items and a specific capacity. You fill this table systematically, starting from smaller subproblems and moving to larger ones. By the time the table is complete, it encodes the optimal solution as the result of many smaller, optimal choices. In knapsack tabulation, each cell in the table is computed using results from earlier cells to decide whether to include the current item. If you skip the item, you simply reuse the best value already found for the same capacity using previous items. If you include the item, you add its value to the best value achievable with the remaining capacity, which is also stored in the table. The value in the current cell is the maximum of these 2 options. In Python, this is implemented with nested loops over items and capacities, filling the table in an order that ensures all needed values are already available, making the method efficient and systematic. When you practice knapsack tabulation, think of the table as modeling real choices, such as selecting research projects within a budget or scheduling data backups within a fixed time. Each entry in the table represents the best possible outcome for a specific budget or time limit and a particular subset of options. As you fill in the table, the final entry gives you the optimal plan under all constraints. With practice, you will become comfortable choosing table dimensions, setting base cases, and defining the update rules so that your Python implementation correctly mirrors the logic of the knapsack problem. Python code. Knapsack tabulation basics. This lesson demonstrates how to solve the knapsack problem using a bottom-up dynamic programming table. We build the table from smaller subproblems, where each cell depends on values from earlier rows or columns that represent choices with fewer items or lower capacity. As we fill in each cell, we decide whether including the current item improves the total value compared to excluding it, based on these previously computed entries. After completing the table, for a small knapsack example, we read off the final table and identify the optimal value from the last cell, which represents the best possible solution for the full problem. The comment explains that installing NumPy Matplotlib and Seaborn is not necessary when working in Google Colab because these libraries are already available there. It serves as a reminder for users running the code on their own machines to install these tools first. These libraries are important for data manipulation and visualization, which support dynamic programming examples such as the knapsack problem used in the script. We begin by setting up two lists, one that stores the weights of items in pounds and another that stores their corresponding values in dollars. Each position in the weight list matches the same position in the value list, so every item has a specific weight and value. These lists provide the essential data for the knapsack problem, allowing us to search for the best combination of items that gives the highest total value without going over the knapsack's weight limit. We set the knapsack's maximum capacity to 5 pounds, which means the total weight of all chosen items cannot exceed this limit. This weight restriction is essential because it determines how many items we can include. It also forces us to carefully select which items to pack so that we achieve the highest possible total value without going over 5 pounds. We start by finding how many items we have by taking the length of the weights list. This total number of items is important because it tells us how large our dynamic programming table needs to be. Each item is assigned to a row in the table, so we can go through them one by one and evaluate how each item contributes to solving the knapsack problem. To apply dynamic programming, we first build a table where each row corresponds to an item, plus an extra row for the case with no items, and each column represents a possible capacity from 0 up to the maximum. Every cell in this table is initially set to 0, meaning no value is achieved yet for any combination of items and capacities. This structure lets us systematically fill in the table as we consider each item and capacity, gradually recording the optimal value achievable for each case. We use a bottom-up dynamic programming approach by filling the table row by row. For each item, we must account for Python's zero-based indexing. This means we subtract 1 from the item number to get the correct position in the lists of weights and values. Doing this ensures we always reference the correct item when performing our calculations in the table. We use the item's index to look up its weight from the weights list, so we can easily reuse that value in later calculations. Using the same index, we also look up the item's value from the values list. Having both the weight and value extracted in this way makes them straightforward to access and use in the dynamic programming steps that follow. In this step of the knapsack dynamic programming algorithm, we go through each possible capacity from 1 pound up to the maximum. For each capacity, we first consider the choice of not taking the current item. In that case, we simply keep the best value that was already computed for this capacity using only the previous items. This value is stored in the dynamic programming table at the row for the previous item and the current capacity. By doing this for every capacity and item, we build on earlier subproblems to eventually find the optimal total value for the knapsack. The algorithm starts by setting the variable that represents taking the current item to 0, meaning the item is initially treated as not chosen for the knapsack. This default choice creates a baseline where the solution value comes only from previously considered items. From this starting point, the algorithm can then compare whether including the current item given the remaining capacity and earlier results, would produce a better total value than leaving it out. To decide whether to include an item in the knapsack, we first check if its weight is less than or equal to the current capacity. If it fits, we compute the remaining capacity by subtracting the item's weight. We then find the best value achievable with this remaining capacity from the dynamic programming table and add the item's value. Comparing this total with the value of excluding the item tells us whether taking the item gives a better overall value. At this step in the dynamic programming table, we choose the best value for the current cell by comparing two possibilities: skipping the current item or taking it. The skip option uses the best value already computed without this item. The take option adds the item's value to the best value achievable with the remaining capacity. We then store the larger of these two results in the current cell, so each cell records the optimal decision up to that point. The code first prints a header that summarizes the problem setup for the knapsack task. It shows the weights of the items in pounds, their values in dollars, and the total capacity of the knapsack in pounds. This header gives a clear overview of the data being used and helps the reader understand the context for the dynamic programming solution that follows. We start by printing a brief header that explains the dynamic programming table, which records the best value for each subproblem, with rows for items and columns for capacities, including capacity 0. Then we go through each row of the table and print it on a single line. This simple layout keeps the output compact and readable, and makes it easy to see the computed values for every combination of items and capacities at a glance. The program outputs the maximum total value that can be achieved with the available items and the knapsack's weight limit. This value is stored in the final cell of the dynamic programming table, which represents the solution to the complete problem. By reading this cell, the code retrieves the optimal result based on including or excluding items without exceeding the capacity. This final value is then printed to show the outcome of the dynamic programming approach. This script solves the knapsack problem using dynamic programming with a tabulation method. It builds a table where each row corresponds to an item and each column to a possible capacity, starting from 0. For every item and capacity, it decides whether to skip the item or include it if it fits, and records the best value achievable. By filling in all these subproblems, the final cell of the table gives the maximum total value that can be obtained for the given weights, values, and overall capacity, which is then printed as the optimal solution. Edit distance, dp. Edit distance measures the minimum number of single-character insertions, deletions, or substitutions needed to change one string into another. It is important in tasks like spell checking and DNA analysis. To compute it efficiently, we use a table where each cell stores the minimum edits required for prefixes of the two strings. By building this table from smaller prefixes up to the full strings, we solve each subproblem once and obtain the overall minimum edit distance. To implement the edit distance algorithm with tabulation in Python, you build a matrix slightly larger than the two strings to include empty prefixes. You initialize the first row and column to represent the cost of converting between empty and non-empty prefixes using insertions and deletions. Then, for each cell, you compare the corresponding characters. If they match, you carry over the previous cost. If they differ, you take the minimum cost of insertion, deletion, or substitution from neighboring cells and add 1. The value in the bottom right cell gives the minimum edit distance, and the matrix as a whole records the steps needed to transform one string into the other. Tabulation is an effective way to compute edit distance, where typos in a search query become substitution costs and missing or extra characters become insertion or deletion costs. The completed table gives both the final distance and a way to trace back the optimal sequence of edits, which helps you visualize how one string transforms into another. For long strings, such as genomic sequences, you can save space by storing only 2 rows of the table at a time. It is best to first practice with the full matrix to build a solid understanding before switching to this more space-efficient method. Python code, edit distance dp. This task is about demonstrating the edit distance algorithm using dynamic programming with a bottom-up tabulation approach. You should build the dynamic programming table step by step for 2 short example strings, showing how each cell is filled based on previous values. After constructing the full table, you then report the final edit distance between the 2 strings. To make the result easy to understand, you also present the completed table in a compact form along with the final distance value. This comment line suggests installing several popular Python libraries used for data analysis, machine learning, and scientific computing. It mentions tools for numerical operations, plotting, statistical visualization, and both traditional and deep learning models. The libraries include options for general machine learning, as well as deep learning frameworks. The comment indicates these packages could be helpful for running or extending the code, even though they are not directly used in the current script. To compute the edit distance between 2 words using a tabulation matrix, we first define a function that takes the 2 words as input. We then determine the length of each word, including the possibility of an empty prefix. This information is used to set the size of the dynamic programming matrix. The matrix will store intermediate results that allow us to systematically build up the final edit distance. To compute edit distance with dynamic programming, we first create a 2-dimensional matrix whose size is based on the lengths of the 2 input strings, plus 1 to include the empty prefix. This matrix stores intermediate results for every pair of substrings from the 2 words. Each cell records the minimum number of operations needed to transform the substring of the first word into the corresponding substring of the second word. By filling in this matrix systematically, we can determine the overall edit distance between the 2 full strings. To begin filling the dynamic programming matrix, we initialize the first column to represent the cost of deleting characters from the first string to match an empty second string. Each row corresponds to a position in the first string, including the empty prefix. For every row, we set the first column entry equal to the row index. This means that transforming the first string into an empty string requires deleting all characters up to that position, so the cost increases by 1 for each additional character. To begin filling the dynamic programming table, We initialize the first row to represent the cost of inserting characters into the first string to match the second string. Each column in this row corresponds to a position in the second string, starting with an empty position. We set the value in each column equal to its column index. This means the cost of turning an empty string into the first few characters of the second string is simply the number of characters inserted so far. To compute the minimum edit distance between two words, we fill in a matrix by scanning through each row and column. At each cell, we compare the current characters from both words. If they match, we copy the value from the diagonal cell above and to the left, meaning there is no extra cost. If they do not match, we consider three operations: inserting a character, deleting a character, or substituting one character for another, each adding a cost of 1 to a neighboring cell. We then take the smallest of these three costs for the current cell, which allows the matrix to capture the minimum number of edits needed to transform one word into the other. At each step of computing the edit distance, we choose the minimum cost among insertion, deletion, and substitution. The insertion cost comes from the cell to the left plus 1. The deletion cost from the cell above plus 1. And the substitution cost from the diagonal cell plus 1. We compare these three values and assign the smallest one to the current cell in the dynamic programming matrix. This ensures that each cell stores the minimum number of edits needed to transform the substring of the first word into the substring of the second word up to that position. At the end, the function returns two results: the full dynamic programming matrix and the final edit distance. The matrix records all the computed costs of transforming one word into the other. The edit distance value summarizes this by giving the minimum number of operations needed for the transformation. Returning both lets the caller see the detailed step-by-step costs as well as the overall result. To illustrate how the edit distance algorithm works, we use the short words cat and cart. We treat cat as the starting word and cart as the target word. The algorithm then determines the minimum number of operations needed to turn cat into cart. These operations can include inserting a character, deleting a character, or substituting one character for another. We use a dynamic programming function to compute the edit distance between two words. When called with the two words, it returns both the dynamic programming matrix and the final edit distance. The matrix shows how the distance is built up step by step, and the final value tells us the minimum number of operations needed to transform one word into the other. We begin by displaying the first word and the second word to show the inputs used in the edit distance calculation. Then, we print the computed edit distance value, which is the smallest number of single character changes needed to turn the first word into the second. Presenting the two words together with this value gives a clear summary of both the inputs and the result of the computation. To set up the dynamic programming table for edit distance, we first create a header row. This row starts with a blank space to represent the empty prefix, followed by each character of the second word. This layout shows how the table's columns line up with the characters of the second word. We then print this header row so it serves as a clear reference when interpreting the table and the operations used in the edit distance calculation. We iterate over each row of the matrix using both the row index and its values, and assign a prefix character to each row. For the first row, this prefix is a space to represent an empty prefix. For all other rows, the prefix is the character from the first word at the position one less than the current row index. We then print each row as the prefix character followed by the row values, which visually aligns every row of the dynamic programming table with the corresponding character from the first word. This script uses dynamic programming to compute the edit distance between the words cat and cart. It builds a matrix where each cell stores the minimum number of operations needed to turn part of the first word into part of the second. The matrix is initialized to account for basic insertions and deletions, then filled by comparing characters and choosing the lowest cost among insertion, deletion, or substitution. The final result shows an edit distance of 1, meaning the words differ by a single character. And the completed matrix illustrates how this value is derived, step by step. Grid paths, tabulation. To count how many ways a robot can move through a grid when it can only go right or down, you can use a table where each cell stores the number of paths from the start to that position. You fill in this table row by row or column by column, using the fact that any path to a cell must come from the cell above it or the cell to its left. By computing each cell once and reusing those results, you avoid recursive calls and make the process more efficient. To use this grid navigation method, you create a two-dimensional array that matches the grid and first set the base cases. If you can only move right or down, every cell in the top row has exactly one path from moving right, and every cell in the left column has one path from moving down. You then fill in the remaining cells so that each value is the sum of the paths from the cell above and the cell to the left. By the time you reach the bottom right corner, this process has computed the total number of paths without repeating any subproblem calculations. This grid-based tabulation method can be extended to handle more complex cases, such as grids with obstacles or cells that have special movement costs. Blocked cells are treated as having 0 paths and are simply skipped in the calculations, much like avoiding walls. This approach is valuable in areas like logistics, emergency planning, and video game pathfinding, where you need to count possible routes or find optimal paths under constraints. By practicing this pattern, you learn to convert spatial problems into structured tables and use local cell relationships to efficiently build global solutions. Python code, grid paths, tabulation. We will count the number of paths through a grid using bottom-up dynamic programming with a tabulation approach. Each cell in the grid will store how many distinct ways there are to reach that position from the starting point, based on the values of neighboring cells. By filling in this table step by step, we can see how the counts build up across the grid. For a small warehouse-style layout, we will complete the entire table, then read off the total number of possible paths from the value in the final cell. The commented line about installing NumPy, Matplotlib, and Seaborn with pip is not needed when you are working in Google Colab, because these libraries are already installed there by default. It mainly serves as a reminder for situations where you run the code outside of Colab. In those other environments, you might need to install these libraries manually before the code will work. We begin by using the NumPy library, which is designed for efficient work with arrays and numerical calculations. In this setting, NumPy helps us build and manipulate a grid that represents the warehouse layout. With this grid in place, we can apply dynamic programming methods to compute how many different paths move through the warehouse. This combination of NumPy and dynamic programming lets us handle the path counting problem in a structured and efficient way. We begin by defining the size of the grid that represents the warehouse using the number of rows and columns. In this example, the grid has 3 rows and 4 columns. This grid will serve as a table that models the warehouse layout. Using this model, we can calculate how many different paths a robot can take to move from the entrance to the exit. We begin by creating a grid as a table of zeros using a numerical library. Each cell in this table starts with a value of 0, meaning the number of paths to that cell has not been determined yet. The table's dimensions are set by the chosen number of rows and columns so that it matches the size of the warehouse grid. This grid will then be used to store the computed number of paths to each position. We begin by setting the value of the top left cell of the grid to 1, because there is exactly one way to be at the starting position by starting there. This step initializes our dynamic programming table and acts as the base case. From this single known value, we can then systematically compute how many paths lead to every other cell in the grid. To fill the first row of the grid, we assume the robot can only move to the right from the starting position. We loop through the columns in that row, beginning with the second column. For each cell, we set its number of paths equal to the number of paths in the cell directly to its left. This way, each cell in the first row accumulates the path count from left to right, reflecting only rightward movement. We now focus on filling the first column of the grid, where the robot can only move downward from the starting position. Beginning from the second row, we loop through each row and set the value in the first column to match the value in the cell directly above it. This way, each cell in the first column accumulates the total number of paths from the top. It reflects the fact that there is only one possible direction of movement in this column, which is straight down. We complete the grid by using dynamic programming, moving through each row and column starting from the second ones. For every cell, we compute how many paths lead to it by adding the number of paths from the cell above and from the cell to the left. By repeatedly combining these previously computed values, each cell ends up storing the total number of ways to reach that position from the starting point. This systematic process builds the full solution step by step across the grid. The code prints a table that shows how many different routes lead to each location in the warehouse grid. Each cell in the table contains the number of ways to reach that position, computed using dynamic programming. By looking at this table, you can see how the number of possible paths builds up as you move through the grid. This visual output helps you understand how the path counts accumulate from one cell to the next. To find the total number of paths from the entrance to the opposite corner of the warehouse, we look at the values stored in the bottom right cell of the grid. This value represents the total count of all possible routes that reach that corner when we are only allowed to move right or down. We then convert this value into an integer so it is easy to read. And finally, we display it as the total number of ways to traverse the grid from start to finish. This script uses dynamic programming to count how many paths exist through a grid when you can only move right or down. It sets up a grid with 3 rows and 4 columns, starting with 1 path at the entrance. The first row and first column are filled by carrying forward that path count, since there is only one way to reach those cells. Every other cell is then assigned a value equal to the sum of the paths from the cell above it and the cell to its left. This process gives the number of possible routes to every position in the grid, and the bottom right cell shows that there are 10 total paths from the entrance to the exit. Optimizing DP tables. Space-efficient tables. In dynamic programming with tabulation, a major concern is how much memory the table uses as the input size grows. A full bottom-up table often stores the entire state space, even though many of those values are not needed later. In many problems, such as computing the minimum cost to reach each step in a staircase, each new value depends only on a few recent values. By keeping only these necessary previous results instead of the whole table, we can greatly reduce memory usage while still computing the correct answer. To make dynamic programming tables more space-efficient, focus on how each new state depends on past states and keep only the minimum needed. If each state only relies on the previous row, you can reuse a small number of rows instead of storing the entire table. This is similar to tracking just the current and previous day's inventory in logistics, or using only recent data in financial forecasting while summarizing older information. By carefully tracing which entries are actually accessed, you can often replace a large table with a rolling buffer or even a single array, greatly reducing space complexity. When designing space-efficient tables, you must update values carefully so the recurrence logic remains correct. The order in which you traverse the table is important, because you need to use all required values before overwriting them. This often means iterating in a specific direction, such as from right to left, to avoid losing entries you still need. When done correctly, this approach lets algorithms handle large data sets efficiently while staying within typical memory limits. Python code. Space-efficient tables. We will use a Fibonacci-style stair climbing problem to demonstrate space-efficient dynamic programming. First, we compare a full dynamic programming table that stores all intermediate results with an approach that keeps only a small, rolling set of values. This shows how both methods compute exactly the same answers for the stair climbing counts, but the rolling version uses much less memory. External libraries are not needed here because the standard environment already includes what we require. To solve this problem with dynamic programming, we define a function that takes the total number of steps as input and returns how many distinct ways there are to climb them. If the number of steps is 1 or less, the function immediately returns 1, since there is only a single way to climb such a small staircase. Otherwise, we create a list to store the number of ways to climb each possible step count up to the target. This list is filled with zeros at first. Then we set the entries for 0 steps and 1 step to 1, establishing the base cases used to build up the rest of the solution. The algorithm fills a table starting from the 3rd step up to the total number of steps. For each step, it computes how many ways you can reach it by adding the ways to reach the 2 previous steps, since you can arrive from either of those. It stores the sum in the current position in the table. After the loop finishes, it returns the value in the last position, which gives the total number of ways to climb the given number of steps. We define a function to count how many ways you can climb a staircase while using very little memory. If the staircase has one step or fewer, we immediately return 1, since there is only a single way to climb it. For larger staircases, we keep track of just the last 2 results, each starting at 1, instead of storing all previous values. By repeatedly updating these 2 values, we can efficiently compute the total number of ways to climb the staircase without building a full table. To compute the number of ways to climb a given number of steps, we loop from the second step up to the final step, updating 2 rolling values that represent the counts for the previous 2 steps. At each step, we find the current count by adding these 2 previous counts. We then shift the older value forward so that the more recent count becomes the new reference for the next iteration. After the loop finishes, the most recent value holds the total number of ways to climb the specified number of steps, and that is what we return. We use a helper function to estimate how much memory 2 different methods will use. We assume each integer takes about 28 bytes, which is a rough but useful approximation. For the full table method, we find the memory usage by multiplying this number of bytes per integer by the total number of integers stored, which is the step count plus 1. This product gives us the total memory required for the full table approach. The code estimates memory usage for a space-efficient dynamic programming method. It assumes each integer takes about 28 bytes, and since the optimized version only keeps 3 integers at any time, it multiplies this size by 3 to get its total memory use. It then returns both the memory estimate for the full dynamic programming table and for the space-efficient version, so they can be easily compared later. We consider a staircase with 100 steps, representing a moderately large problem size, and we want to find how many different ways there are to climb it. To do this, we use a dynamic programming approach that builds a complete table of the number of ways to reach each step. The function that implements this method fills in the table step by step and then returns the final count for the top of the staircase. We store this final count as the overall result for the full dynamic programming solution. We first compute the number of ways to climb the stairs using a space-efficient method that keeps only the last 2 results instead of storing all previous values. This rolling approach greatly reduces memory use while still giving the correct count. We then estimate how much memory each method uses by calling a helper function that returns the memory in bytes for both the full table and the space-efficient versions. Comparing these 2 values shows the difference in their memory footprints. The program first prints the number of ways to climb the stairs using the full dynamic programming table, which serves to confirm that this method works correctly. It then prints the number of ways using a more space-efficient approach. By comparing these 2 outputs, we can check that both methods give the same result. This matching result confirms that the space-saving method is correct as well. We compare the memory usage of two dynamic programming strategies by printing their approximate memory consumption. The first method stores a full table of intermediate results in a list, which uses more memory. The second, space-efficient method uses rolling variables and keeps only the last two computed values, greatly reducing memory use. These measurements highlight how different computational strategies can trade off memory usage while solving the same problem. The code computes a space-saving factor by dividing the memory used by the full table method by the memory used by the space-efficient method. This ratio shows how many times less memory the efficient version requires. The result is rounded to 2 decimal places for readability, then printed to clearly compare the memory efficiency of the two approaches. This script compares two dynamic programming methods for counting how many ways you can climb a staircase. One method stores the result for every step in a full table, while the other keeps only the last two results using rolling variables. Both methods produce the same answer, even for a staircase, with 100 steps, confirming they are correct. However, the rolling variable method uses far less memory, storing only a few integers instead of over 100, which makes it roughly 30 times more space efficient. This highlights the benefit of using space-efficient, dynamic programming when only recent results are needed. Eliminating redundant states. Eliminating redundant states in a dynamic programming table means checking whether each computed cell is actually needed to obtain the final answer. A state is redundant if its value is never used or can be derived from other stored values without keeping it explicitly. Many initial dynamic programming formulations are overly large, including indices or parameters that do not matter in practice, such as time steps beyond any realistic deadline in a scheduling problem. By carefully examining the problem constraints and how states transition, we can shrink the state space, which reduces memory usage and speeds up the algorithm without changing the result. When simplifying dynamic programming, focus on which states are actually needed. First, check reachability. If a state cannot be produced from the starting conditions, it can be ignored. For instance, some combinations of budget and projects may be impossible, so those states are skipped. Next, check dominance. If one state is always at least as good as another in every relevant way, the weaker state is unnecessary. By removing both unreachable and dominated states, you reduce the table to only the states required for finding an optimal solution. To remove redundant states in a dynamic programming table, match the table's detail level to the actual precision the problem needs. In applications like inventory management or route planning, you usually do not need to represent every possible quantity exactly. Instead, you can group similar values, round measurements, or cap extreme capacities that do not change the decisions. This shrinks the table while preserving solution quality and keeps the algorithm efficient within practical computational limits. Python code, eliminating redundant states. Use a simple knapsack-style problem to show how we can eliminate redundant dynamic programming states. First, compare a naive table that tracks every possible capacity with an optimized table that only considers capacities that are realistic for the given items. Then explain that many capacities are unreachable based on item sizes, so we can safely prune them. This pruning reduces the number of states we store and update, which in turn cuts both memory usage and computation time while preserving the correct result. A line that starts with an exclamation mark is often used in a notebook environment to install a package, but here it simply acts as a placeholder. It indicates that no extra packages need to be installed. The message is that the code uses only standard Python libraries, so it is self-contained and has no external dependencies. The script starts by importing the time module so it can measure how long the code takes to run. This timing information is useful for comparing the performance of different algorithms or configurations. In this case, it is used to record and compare the execution time of the naive and optimized dynamic programming solutions to the knapsack problem. This allows a clear assessment of which approach is more efficient. We begin with two lists. One records the weights of items in pounds, and the other records the corresponding values of those items in dollars. Each position in the weight list matches the same position in the value list, so every item has a defined weight and value. This setup is typical of a knapsack problem, where we want to choose a combination of items that gives the highest total value without going over a specified weight limit. In this example, we set an unrealistically large maximum capacity of 50 for the naive dynamic programming table. This high value is chosen on purpose to show that the naive method considers every possible capacity, even ones that cannot actually occur given the item weights. As a result, the table includes many unnecessary states. This highlights how inefficient the naive approach can be, because it spends effort on capacities that do not help solve the problem. To set a realistic maximum capacity for the knapsack problem, we add up the weights of all available items. This total represents the largest capacity that can actually be filled using those items. By limiting our dynamic programming table to capacities up to this value, we avoid considering impossible states. This reduces redundant computations and makes the algorithm more efficient. The naive knapsack function builds a dynamic programming table that considers every capacity from 0 up to the maximum, even capacities that cannot actually be reached. It creates a grid with one row for each item, plus an extra initial row, and one column for each possible capacity, all starting at 0. For each item and each capacity, if the item fits, it compares the value of taking the item, which adds its value to the best value for the remaining capacity, with the value of skipping it, which keeps the previous best for that capacity. It stores the larger of these two values in the table. And if the item does not fit, it simply copies the previous best value. The final answer, the best value for the full capacity, is read from the bottom right cell of this table. We build an optimized dynamic programming table to solve the problem for a given capacity limit. The table has one extra row for 0 items and one extra column for 0 capacity, and each cell stores the maximum value achievable with a certain number of items and a certain capacity. For each item and each capacity up to the limit, we decide whether to include the item or skip it. If the item fits, we compare the value of taking it, which is its value, plus the best value for the remaining capacity, with the value of not taking it, which is the best value from the previous row. If the item does not fit, we simply copy the best value from the previous row. The final answer is the value in the last cell, which represents the best value achievable with all items and the full capacity. To measure how long the naive dynamic programming solution for the knapsack problem takes, we first record the current time using a timing function. We then run the naive knapsack procedure with the given weights, values, and maximum capacity, and store the best value it returns. After the computation finishes, we record the current time again. By subtracting the start time from the end time, we obtain the total running time of the naive approach. We begin by recording the current time so we can measure how long the optimized dynamic programming version of the knapsack algorithm takes to run. Then, we call the optimized knapsack function with the item weights, their values, and a realistic maximum capacity. This function computes the best possible total value while avoiding unnecessary capacity calculations. After it finishes, we record the end time and use the two timestamps to find the total execution time. This measured time is then used to compare the efficiency of the optimized approach with the naive version. To compare the naive and optimized dynamic programming tables, we first count how many states the naive table has by multiplying the number of items plus 1 by the naive maximum capacity plus 1. This gives the total number of possible states, including many that are never actually needed. For the optimized table, we instead multiply the number of items plus 1 by the realistic maximum capacity plus 1. This focuses only on capacities that can really occur, reducing the number of states and making the computation more efficient. The code compares results from two dynamic programming methods for the knapsack problem. It first prints the maximum value found by a naive approach using a capacity that is larger than necessary. It then reports how many states this naive method used, which corresponds to the size of its dynamic programming table. Finally, it shows the computation time, rounded to 6 decimal places, to emphasize how inefficient the naive approach becomes when the capacity is unrealistically large. The program reports the results of the optimized knapsack solution by printing the maximum value found, how many states were used, and how long the computation took. These outputs show that the optimized method avoids unnecessary states and focuses only on realistic capacities. As a result, it reduces computation and runs more efficiently than a non-optimized approach. This line prints a brief explanation of how removing unnecessary capacities from the dynamic programming table improves performance. By discarding capacities that are larger than any realistic value, the table becomes much smaller. As a result, the algorithm needs less memory and runs more efficiently. This script shows how to speed up a dynamic programming solution to the knapsack problem by removing unnecessary states. It compares a naive version that uses an unrealistically large capacity with an improved version that limits the capacity to the total weight of all items. Both versions compute the same maximum value for the given weights and values, but the optimized one tracks far fewer states. As a result, it runs faster and uses less computation, illustrating the benefit of pruning capacities that can never be reached. Memoization versus tabulation. Memoization and tabulation differ in how they explore a problem's state space. Memoization starts from the original problem, recursively visits only the subproblems that are actually needed, and caches their results. So its running time depends on how many states are reachable and how costly each is to process. This can be efficient when many possible states or paths are never used. Tabulation instead builds a full table of all states within predefined bounds, which makes its time complexity easier to express in terms of the table's dimensions. However, this can do extra work when the state space is sparse or many of those states are never relevant. Memoization uses space only for states that are actually visited, which is efficient when the theoretical state space is huge, but constraints mean you only ever need a small subset, such as only feasible task combinations in a scheduling problem. In contrast, tabulation allocates a full table over the entire range of state variables, which can waste memory when many entries are never used. However, because tabulation fills this table in a regular, predictable way, it supports systematic space optimizations, like reducing or compressing dimensions. So memoization is naturally space efficient in sparse state spaces, while tabulation can be more memory heavy, but easier to optimize structurally. When optimizing performance, the choice between memoization and tabulation is a trade-off between adaptivity and regularity. Memoization adapts to the actual search space of the input, which can be helpful in tasks like game evaluation, but it depends on recursion and can introduce overhead and irregular memory access. Tabulation, instead, uses simple loops over arrays, avoids recursion, and makes worst-case behavior easier to analyze. This regular structure also enables systematic optimizations, such as rolling arrays. To use each method effectively, you should consider how many states you need and how predictable the access pattern will be. Python code: memoization versus tabulation. This lesson compares memoization and tabulation as two dynamic programming strategies. It explains how memoization only stores and revisits states that are actually needed, while tabulation fills an entire table of possible states. You will see how the number of visited states and the size of the table influence both time and space usage. Finally, the program prints the results and operation counts for each method so you can directly compare their performance on the same problem. This script does not require any pip install commands because it uses only Python's standard libraries. All the needed features come from built-in modules that are already included with Python. As a result, the script is easy to run and remains widely compatible without extra setup or additional installations. We begin by importing the functools library so we can use its memoization decorator on our recursive Fibonacci function. Memoization improves performance by storing the results of previous function calls. When the function is called again with the same input, it reuses the stored result instead of recalculating it. This avoids redundant work and makes the Fibonacci computation much more efficient. We begin by creating a dictionary called the call counter to track how the Fibonacci function behaves. One entry records how many times the function is called, starting at 0. But another entry is an empty set that will store each distinct input value the function receives. By updating these two parts as the function runs, we can see both the total number of calls and how many unique states or inputs are processed during execution. We use a least recently used cache from the standard library to store and reuse Fibonacci results, so we do not recompute the same values. Each time the function runs, we increment a counter to track how many calls are made and record the current index in a set of visited states. For the base cases, when the input is 0 or 1, the function simply returns that input, since these are the first two Fibonacci numbers. For all other inputs, it returns the sum of the results for the two previous indices, relying on the cached values to make the recursive computation more efficient. This approach computes Fibonacci numbers using a bottom-up dynamic programming method called tabulation. If the input is 0 or 1, we simply return that value as a base case. For larger inputs, we create a list of size n plus 1 to store all Fibonacci values up to the nth position, starting with 0 and 1 as the first two entries. We then move from the second index up to n, setting each entry to the sum of the two previous entries. The final result is the value stored at position n in this list, which is the desired Fibonacci number. We choose the value of n to be 20 so that the results are easy to read and the program runs quickly. This value is large enough to show how the algorithms work in practice, but not so large that it slows down computation. In this way, setting n to 20 provides a good balance between demonstrating efficiency and keeping execution time reasonable. To compute a Fibonacci number efficiently, we use a memoized Fibonacci function that starts with the full problem size n. This function stores previously computed values so it does not repeat the same calculations. As it works recursively, each needed smaller Fibonacci value is solved once and then reused from the cache. The final result, which is the Fibonacci number for the given n, is stored as the memoized result. We compute a Fibonacci number using the tabulation method by filling a table from the bottom up. Starting with the smallest Fibonacci values, we iteratively calculate each next number in order. This ensures every value is computed only once, making the process efficient. The final Fibonacci number we need is then stored in a variable for later use or comparison. We are measuring how many unique states are visited while computing the Fibonacci sequence with memoization. A set stored in the call counter keeps track of all the indices that were actually computed. By taking the size of this set, we find how many distinct Fibonacci numbers were calculated instead of retrieved from the cache. This number shows how many unique subproblems were solved and helps us understand the efficiency of the memoized approach. We display the input value used for the Fibonacci calculation, then show the results produced by the memoization approach and the tabulation approach. Presenting these side by side lets us directly compare how both dynamic programming methods solve the same problem size. This comparison helps confirm that they produce the same Fibonacci number for a given input. We report two key statistics for the memoized Fibonacci computation. First, we print the total number of recursive calls, which shows how many times the function was actually invoked. Then we print how many distinct states were visited, meaning how many unique Fibonacci values were computed and stored. Comparing these numbers reveals the efficiency gained by memoization, since many potential repeated calculations are avoided. For the tabulation approach, we report two key statistics. First, we print the size of the table, which is the total number of possible states from 0 up to n, giving n plus 1 entries. Then, we print how many of these states were actually filled. In this case, the number of filled states is also n plus 1, meaning every possible state in the table was computed. This script compares two dynamic programming methods for computing Fibonacci numbers: memoization and tabulation. Both are used to calculate the 20th Fibonacci number, but they manage computation differently. Memoization uses recursion with caching to avoid repeated work and reports how many function calls it makes and how many distinct states it visits. Tabulation builds the answer iteratively from the base cases up, storing intermediate results in a table and reporting the table size, which covers all states from 0 to 20. The two methods produce the same Fibonacci value, but highlight different trade-offs in time and space efficiency between recursive caching and iterative table building. In this lecture, you learn to design bottom-up DP tables that capture subproblem states and transitions, implement tabulation-based dynamic programming algorithms in Python for classic problems, and analyze and optimize the time and space complexity of tabulation solutions. In the next module, Module 9, we will go over graphs and traversal.
Thank you for your attention. See you all in the next lecture.